Welcome back to our heat transfer class, where we are delving into the phenomenon of the exchange of thermal energy between surfaces by radiation. This video was made with the support of InnoEnergy. After studying the behavior of ideal surfaces, in this lesson we will study the behavior of real surfaces as a deviation from ideal behavior. We will divide this lesson into several parts. The objective is to analyze the radiant energy emitted by a non-ideal surface, as well as the absorption and reflection of radiation by non-ideal surfaces. To do this, let's first go to the laboratory to extract some experimental evidence. Let's start by measuring the emission. We have an emitter and a receiver. We take a black surface as a reference. We measure the temperature and the radiation emission. We change it to a real surface at the same temperature and we measure the radiation emission. We compare the emission spectrum of the real surface with that of the black surface. The spectral emissivity is the ratio of the spectral emissive power of the actual surface to the spectral emissive power of a black surface at the same temperature. Thus, the actual surface emissive power can be calculated from the black surface spectral emissive power and the spectral emissivity, integrating over the entire spectrum. If the area under the curve is equal to an emissivity per sigma t to the fourth, we have a global average value of emissivity, called total emissivity. The drawback of using this emissivity for calculating the emission of real surfaces is that it depends on the temperature. Values of emissivities at different temperatures for some materials can be found in heat transfer handbooks and texts. The most common is to consider the approximation that the emissivity is constant throughout the spectrum. The curve of a surface of these characteristics is proportional to that of the black body. This type of approximation with constant emissivity is called a gray surface. Once the emission is analyzed, let's see what happens with the absorption. Kirchhoff's law states that if a body is in thermodynamic equilibrium with its surroundings, its emissivity is equal to its absorptivity, both for spectral and total absorptivity. On opaque surfaces, not all of the radiation is absorbed, so some is reflected. The reflection can be specular or diffuse. As an emission, diffuse reflection implies that the reflected energy is uniformly distributed in all directions in space. In this course, we will work with diffuse surfaces, with diffuse emission and reflection. For opaque surfaces, tau is 0. So the sum of the absorptivity and the reflectivity is equal to 1. Let's finally see how we can manage real surfaces with variable emissivity. The gray bands approach consists of dividing the electromagnetic spectrum into bands where the emissivity can be considered approximately constant. Thus, instead of considering a real surface as gray, with a constant value of emissivity for the entire spectrum, we approximate it as a gray surface in fractions of the spectrum or bands. This approximation converts the emissive power curve into a discontinuous curve that attempts to approximate the real curve. Obviously, the higher the number of bands, the better the approximation. Like the mesh for conduction in solids. Thus, the emissive power in a band of the spectrum is the emissivity in that band, which is constant, times the emissive power of a black surface in that band of the spectrum. The area under the curve is no longer an integral but a summation, where n sub b is the number of bands considered.